A little bit more application-y. Example 10, we're dealing with a diver jumping off a board, and that board starts 32 feet above the water, and then we deal with an initial velocity. So we're working with a little bit of physics here. So this is always holds true, right? So this is going to be our position function, and V of O represents the initial velocity, and S sub O represents the initial position. We always use S for position, and we always use V for velocity, so that's pretty normal. So I'm going to go ahead and fill in this equation given the information that I have. The initial velocity was 16 feet per second, so I'm going to go ahead and plug in a 16 there. And then the initial position was 32. So I now have a full equation that I can work with. Now this is a parabola, it's an upside down parabola, which makes sense for the diver. So let's go ahead and do a graph. I've got 10, 20, 20, 30, 40. I'm going to count by tens here. It's okay if your scale is different on the X and Y axis. So I can do that, and then I can count by ones here. That's what I want to do. That's not a problem. So we'll go ahead and set this up as this is your feet, and this is your seconds. So when does the diver hit the water? Well, what's happening is I'm going to start at 32 feet, and then it's going to go up. I don't know exactly where the vertex is, but it's going to go up, right, and then it's going to come down. So the idea is, when is that going to be equal to 0? So I want to know when I land right there, because this is my water. That's what I'm looking for. So this is not a calculus question. This is a situation where I want to know when the position of the diver is equal to 0. So this is an Algebra 2 question. First thing we would want to do is factor out a negative 16. Now you do need to be careful with your signs, because it does flip those signs. So I would end up with negative 16 is equal to t minus 2, right? And then plus 1 equals 0. So it looks like my diver is going to be at position 0 at t equals 2 and at t equals negative 1. But wait a second, y'all. This is an application problem. Time can't be negative. So I'm not going to include that. So t equals 2 seconds is how long it takes the diver to reach the water. So knowing that, I could probably finish this, right? So I know my graph looks something like that. Now I could plug in some points and actually find the exact shape of the parabola or the exact vertex. That wouldn't be a big deal. But I just wanted you to get a general feel for that. So let's do a little bit of calculus now. Find the instantaneous velocity at t equals 1. So I want to know the velocity at t equals 1. That means I want the derivative of position. That's velocity. Okay, the derivative of position, the rate of change of position, is velocity. So we're going to use the power rule. So I'd end up with negative 32t and then plus 16. So that's the equation that would give me any velocity at any time, but I want to know S prime of 1. You notice that I use the correct notation here, okay? You do need to label this. You can't just have this with no label. That matters. But now I'm going to label it as S prime of 1, which is V of 1. Okay, I would really like here early on for us to connect these. This is the first time that we've done this in this class, so we want to make sure that we connect that is the derivative of position is equal to velocity. So when I plug in a 1 for my time, I end up with negative 16. You better have a unit attached to that. This is a rate of change, so I'm doing the slope. So it is still the change in y over the change in x. So the unit would be feet per second. Right? So that means that the position of the diver, right? So this is used to represent the position. The position of the diver is decreasing, right? So I'm getting closer and closer and closer to the water, right? So I'm going at negative 16 feet per second. Okay. The distance between the diver and the water is decreasing at that point at t equals 1. All right, the average velocity. Let's go ahead and take one last look at this. The average velocity is just a slope formula, right? F of B minus F of A over B minus A. In this case, it's S because we're dealing with position. Average velocity and instant velocity are slightly different. So we're going to do s of 2 minus s of 1 over 2 minus 1. We don't have a specified notation for this. Okay, this is just an average. So if you want to put average velocity equals, that's fine, but we don't necessarily have a specified notation. So we would take these values, we would plug those in, right? So I would plug in a 2 into my position function, I would get 0. I would plug in a 1 into my position function, and I would get 32. So that's how high I was. So remember, you have to have your difference quotient. So you either have to have this piece or this piece. One of those two has to be shown, but you do have to have the difference quotient. So this does reduce to negative 32 over 1. So at that exact moment in time, right, I was thinking ahead of myself. At t equals 1, I was at negative 16 feet per second. That was a precise moment in time, but my average velocity over the 1 to 2 seconds was negative 32 feet per second. So that's my average. So that would be the slope between these 2 points, right? So this is the slope of the secant versus the slope of the tangent. I hope that visual helps that make a little bit more sense.